My name is Bernadette Weinzierl. I'm a professor for aerosol physics and cluster physics at the University of Vienna. In my research group, we carry out experiments in the laboratory and on research aircraft. We study the fundamental physical and chemical properties of aerosol particles and cloud particles and their influence on the atmosphere and climate. Global average temperatures have increased by 1.3 degrees in the past century. In the past year, an unprecedented number of heat records have been broken around the world. Anthropogenic emissions of greenhouse gases have reached record levels. It is well known that climate change affects the environment in many different ways. In this video, I would like to show you an unexpected effect, which may sound paradoxical. Air quality has improved significantly over the past decades, but this has made human-made global warming more apparent. Aerosols, tiny particles suspended in air, are a key component of the climate system. They have natural and anthropogenic sources. Examples for aerosol particles are black carbon from burning fossil and biomass fuels or wildfires, sulfide particles or natural mineral dust. Fine particles, so-called PM2.5, and ultrafine particles, together with ground-based ozone, top the list of the harmful pollutants. These air pollutants are responsible for about 13 premature deaths every minute and cause years of suffering for hundreds of millions of people. Many air pollutants are visible components of the atmosphere. Here in the satellite image, pollution over Asia is visible. The photograph shows the emissions from wildfires over the US. And this photograph shows a deep mineral dust layer over the Caribbean. There's so much mineral dust in the atmosphere that the ground is no more visible. While fine particles pose health risks because they are inhaled deeper into the lungs and can even pass into the bloodstream, the impact of aerosol particles extends far beyond human health to complex impacts on environment and climate. What is the role of aerosol particles in the climate system? Aerosol particles scatter and absorb solar radiation. This leads to a cooling at the ground because less energy reaches the surface. Besides this, aerosol particles impact water and ice cloud formation and can modify the properties of clouds. Most important, without aerosol particles, cloud droplet formation would not be possible in the atmosphere. Clouds in a polluted environment have more but smaller cloud particles than the same cloud in a clean environment. This makes polluted clouds appear whiter at the cloud tops and increases the scattering of sunlight back into space. This also impacts the lifetime and precipitation processes of such clouds. How can we now determine the effect of a change in various components of the atmosphere? For this, the concept of radiative forcing was introduced. The radiative forcing is a measure in watts per square meter of the change in the Earth's atmosphere's radiation budget when some parameter is changed. Such a parameter could, for example, be the concentration of aerosol particles or the concentration of greenhouse gases like carbon dioxide, CO2. This graph shows the temporal change in radiative forcing for different constituents of the atmosphere. Whereas greenhouse gases like carbon dioxide or methane cause a warming, aerosol particles and their interaction with clouds and radiation causes a net cooling effect. Locally, aerosol particles can have a warming or a cooling effect, depending on their chemical composition. For example, absorption of sunlight by black carbon can warm atmospheric layers and also change the temperature profile of the atmosphere with various impacts on cloud formation and weather. However, globally, aerosol particles have an overall cooling effect, which compensates or masks part of the warming caused by greenhouse gases, mainly CO2 and methane. In fact, without anthropogenic aerosol particles, average global temperature increase would be about 0.5 degrees higher than what we observe by now. Already in 2005, a study in Nature stated that emission control and efforts to improve air quality will reduce the dimming effect of aerosols and might lead to further warming. Since the 1980s, the European Union has implemented strict measures to reduce air pollution. Emissions of the main air pollutants have decreased drastically. For example, the sulfur oxide emissions dropped by over 93% since 1990. The reduction results from a combination of measures, including fuel switching, flue gas desulfurization abatement technology, EU directives relating to the sulfur content of certain liquid fuel, reduction of sulfur dioxide emissions in shipping fuels, etc., etc. In the atmosphere, sulfur dioxide is converted into sulfate particles that, in high concentrations, contribute to the problem of acid rain. But those sulfate particles also have a cooling effect as they scatter sunlight back into space. This graph here summarizes the radiative forcing caused by anthropogenic greenhouse gases and by aerosol particles. Without the anthropogenic aerosol particles, the total anthropogenic warming would be even stronger. Here is the dilemma. Reducing aerosol emissions improves air quality, prevents people from suffering and saves lives. But it also reduces the particles' cooling effect on the planet. The situation is complex. Emissions of anthropogenic carbon dioxide, methane, and other greenhouse gases increased strongly since 1850 and continue to increase. Most human-made components of the climate system, like carbon dioxide or methane, cause a climate warming. Globally, aerosols have a cooling effect. However, a strong regional differences in particle type can locally cause a cooling or a warming. Without aerosol particles, the observed climate warming would be about 0.5 degrees Celsius stronger. It is important to note that the lifetime of aerosol particles and greenhouse gases in the atmosphere are extremely different. Whereas aerosol particles stay in the atmosphere for weeks, some greenhouse gases like carbon dioxide can stay in the atmosphere for hundreds of years. To understand the changing climate system, aerosol research is important. Measurement data are critical to understand the highly complex physical and chemical processes in the atmosphere and to constrain model simulations. We must be aware that every path we choose has advantages and disadvantages. Protecting the environment and human health does not necessarily mean benefits for the climate. However, improving air quality is key. In the short term, the world will have to accept a little extra warming for cleaner air. Ultimately, we have to solve the real problem and reduce human-made greenhouse gas emissions.